Welcome back. Today, we've got a really interesting problem on our hands. This one's a classic coordinate geometry question, lifted straight from a higher-tier GCSE paper. It's a bit of a brain teaser, so let's get into it.
Okay, so let's take a look at the actual question. Here's the setup. We're given 3 points. 2 of them are fixed, but the third one, well, its coordinates depend on this unknown value, k. And here's the absolute key to the whole thing. We're told these 3 points form a right angle. That's the clue we need to crack this.
So what we're going to do is solve for k. But here's the cool part. We're going to do it using 2 totally different methods. And we'll see how in maths, different roads can often lead to the same destination. We'll even be checking in with the official mark scheme along the way.
Right. First things first. Let's break down exactly what we know.
Okay, so here's the key info all laid out. We've got our point P and our point Q. Those are locked in. But then there's point R, which is a bit of a moving target, right? Its location is totally tied to whatever K turns out to be. And that last point, that's the real game changer. The angle at R is 90 degrees. Everything hinges on that fact.
All right, let's jump into our first method. We're going to call this the gradient method. This all comes down to the idea of how steep the lines are.
Now, you've probably come across this rule before. It's a huge one in coordinate geometry. If you have 2 lines that are perpendicular, meaning they meet at a right angle, then when you multiply their gradients together, you always get -1. So our plan is simple. Find the gradient of the line from P to R, find the gradient of the line from Q to R, and then use this rule to build an equation.
So we just need to use our good old rise over run or change in y over change in x formula. We plug in the coordinates we have, and since r has k in it, our gradients are going to be expressions that also have k in them. That's exactly what we want.
And you know what's great? Just doing this first step, even before you've solved anything, gets you marks on the exam. The official mark scheme literally says for process to find gradients of PR or QR. So showing your work here is absolutely crucial.
Okay, now we've got our 2 gradients. Time to use that rule we just talked about. We take our first gradient, multiply it by our second gradient, and set the whole thing equal to -1. Now, this looks a bit messy with all the fractions, I know. But with a little bit of algebraic shuffling, basically multiplying things out to get rid of the denominators, it simplifies down really nicely into this, a standard quadratic equation. Make a mental note of this one, because we're going to see it again.
Okay, but what if gradients didn't pop into your head during the exam? No worries. There is another fantastic way to solve this, and it uses a theorem that I guarantee you've known for ages.
Yep, it's Pythagoras' theorem. Because we have a right angle at R, the points P, R, and Q form a right-angled triangle. And we all know the rule, a squared plus b squared equals c squared. In our case, that means the length of PR squared plus the length of RQ squared has to equal the length of the hypotenuse, PQ squared.
So we'll use the distance formula to find the length of each side. And really, the distance formula is just Pythagoras in a different outfit. We'll work out an expression for the square of each side's length. For PQ, since we have the numbers, we can work it out completely.
And just like with the gradient method, the mark scheme confirms this is a perfectly valid way to start. It explicitly gives marks for start of process to use Pythagoras, so you're on the right track either way.
All right, time to put it all together. We take our expression for PR squared, add our expression for RQ squared, and set it all equal to the value we found for PQ squared.
Okay, this next part involves a bit of algebra, expanding all those brackets and tidying everything up. But when the dust settles, check it out. We get the exact same quadratic equation we got from the gradient method. How cool is that?
So, this is awesome. 2 completely different mathematical paths have led us to the exact same spot. Now there's only one thing left to do: solve this quadratic equation.
And again, we have choices. You could try to factorize it if you can spot the numbers, or you can always rely on the trusty quadratic formula. Doesn't matter which you choose, both will spit out the 2 possible answers for k.
So after you run the numbers, you'll find that one of the possible values for k is -6.
And the other value for k that makes that angle a perfect 90 degrees is 3.5.
So we got our answers. But what's the big lesson here? For me, it's that true understanding in maths isn't just about getting the right answer. It's about seeing that there are often multiple beautiful ways to get there. The fact that the official mark scheme accepts both the gradient method and the Pythagoras method proves that. It shows that there's flexibility in how you can think about a problem.
So that leads me to a final question for you. Which of those 2 paths made more sense in your head? Was it the gradients or was it Pythagoras? There's no right answer, but thinking about why you prefer one over the other can tell you a lot about your own problem-solving style. Thanks for diving into this with me.